Hello everyone, I'm Jiazhen from Fudan University. Today on behalf of my co-authors to present our work, Efficient Incident Identification from Multi-Dimensional Issue Reports via Meta-heuristic search. In this talk, I will first introduce the background about incident identification from issue reports. Next, I present our meta-heuristic search framework, MID. Then, the evaluation and representative cases are shown to prove the effectiveness and efficiency of our approach. In large-scale infrastructure as a service systems, millions of customer VMs are hosted in worldwide distributed physical servers. As more and more companies come to the cloud system, achieving high availability and reliability is critical but challenging for such systems. In order to minimize the negative customer experience and the potential financial loss, efficiently identify the incidents and isolate the problem is a common request of the system operation. In infrastructure as a service systems, incidents are unplanned bursts of anomalous behaviors of VMs. For example, if we count the total number of interruptions and observe a sudden burst, as the figure shows, we can conclude that an incident happened. Such incidents are typically caused by many factors, including bugs, improper configurations, and software incompatibility. They can downgrade system performance and continuously affect service reliability. In current practice, cloud systems like Microsoft Azure typically monitor the performance indicators such as I/O latency and CPU utilization of VMs. When the monitored indicators exhibit anomalous values, the related information about the anomalous VM would be recorded in an issue report. Here is an example. An issue report typically contains a timestamp recording the time when the anomalous behavior is detected, and there are a lot of categorical attributes describing the VM properties. For a large-scale cloud system, there would be a huge amount of issue reports. So, we can treat a set of issue reports as multi-dimensional time series data. Now, I use an example to demonstrate how to identify incidents from issue reports. In the top level, if we aggregate all anomalous behaviors with respect to each day, we get the corresponding time series. We cannot find any incident from this figure, since the curve is rarely flat from April the 1st to April the 10th. Since each VM can be characterized by many properties, we can use the country column to denote the region that VM allocated. Suppose we want to see the interruption condition in the US region, then we can get this figure. It is different from the previous one. It might have a problem because there is a little bit trend from April the 7th. Let us continue to break down. Now we have the data center column and the corresponding figure for data center DC1. The trend seems to be more apparent. Note that we can have different values for each column. For the specific value, we call it as attribute. Now, these two legends describing the VM properties are referred to as the attribute combinations. Let us break down to the disk type. We find this time series with sudden burst, so an incident is identified. And the attribute combination referring to an incident is called the effective combination. Although the incident cannot be observed in the top levels due to certain noisy issues, we can identify incident while finding effective combinations. However, finding effective combinations from issue reports is not easy. Actually, there are tens of columns in the cloud systems to characterize a single VM, leading to huge amount of possible attribute combinations. So, our goal is to detect incidents from an enormous attribute combinations. It is of fundamental importance because it helps to isolate problems with less missing or false alarms. Furthermore, it provides necessary information for diagnosis. In current industrial practice, many data scientists manually identify the incidents with pivot table. They have many pain points. It requires domain expertise and is usually labor-intensive. Actually, our goal is find effective combinations in the search space. Hence, we can formulate the incident identification problems as a search problem. We decided to develop a systematic and automatic search framework to find effective combinations from issue reports. In the search framework, we first need an effective object function to guarantee that we are on the right way. So, we consider two things for finding incidents: the impact for volume and the significant change. We first define a ratio px to denote the percentage of interruptions of current combination among all interruptions. Then, for each searched combination, we perform change point detection and divide the whole time series into two parts: the part before change point, part B, and the part after the change point, called part A. So, we use PA to reflect the impact for volume, and login PA divided by PB to reflect the change rate, where the login operation is used to normalize the value. Finally, we use the impact for volume multiplied by the significant change as our objective function. A larger objective function value means the incident is more severe. With the objective function, we then need to design the search framework. In the search paradigm, it is very intuitive to perform greedy search for all combinations, which means that it has to search all its subsets before going to a pair set. The complexity is as large as this order. In cloud system context, we have tens of columns, and each column has a lot of attributes. So, the search space can be more than 10 to the 50 power. It is very time-consuming and hence inefficient. We can also choose the random search, which can go anywhere in the search space. However, it is not effective if with an uninformative guide. So, how can we search the results both effective and efficient? We resort to meta-heuristic search. In the proposed heuristic search framework, we employ a two-mode dynamic search strategy, which balances greedy mode and random mode so as to improve efficiency with high effectiveness. We define the scope of each search step as neighbors, including the pair set, subset, and supersets, respectively. For such operators, the add, delete, swap column, and swap value are employed to select the attribute combinations from neighbors. The scoring function is used to guide the choice of search operators in each search step. Since there are no explicit scoring function that can be directly used in our context, we design a new scoring function in the greedy mode based on information entropy. The entropy is defined as the negative logarithm for the probability. Specifically, given an attribute and the set of its values v, the entropy of a value vi can be calculated as the following equation. In the greedy mode, our approach prefers to select the attribute value with larger entropy value and visit the neighbors accordingly. Although the search space in each search step is reduced to the neighbors, there are still a lot of attribute values. Evaluating every single value would cause large overhead and thus cause inefficiency of our search framework. So, in order to reduce the evaluation overhead, we utilize the best from multiple selection strategy to extract a subset consisting of promising candidates to reduce the evaluation overhead and to avoid the local minimum. Furthermore, meta-heuristic search algorithms typically suffer from the cycling problem. So, during the search, we maintain a forbidden list consisting of recently visited solutions. so we can avoid the revisiting problem. In the experiments, we evaluate our approach with both synthetic issue reports and real production issue reports from Microsoft. The synthetic datasets are generated with different total number of attributes, from small to large, and we use precision, recall, and F1 score as the performance metrics. For real datasets, the large-scale multidimensional issue reports cause it hard to manually identify and verify all effective combinations, so we lack ground truth about the real datasets. And to these real datasets, we manually check the results and compare the total number of identified incidents. And in the experiments, we try to answer the two research questions. Is our approach effective? And how efficient is our approach? For the first research question, we compare the performance of our approach with the state-of-the-art approach, IDES, two other heuristic search methods, and the random search. The results are shown in the tables. For all synthetic datasets, our approach achieves the highest F1 score, and for the real issue reports, our approach finds most incidents on 9 of 12 datasets. As for the rest 3 datasets, the results of our approach are much close to the best. So, we can conclude that our approach is effective in identifying incidents for both synthetic and real datasets. We also evaluate the execution time of different methods on synthetic datasets and real-world datasets. The results show that despite the smallest synthetic dataset, our approach outperforms all other methods, which proves the high efficiency of our approach in identifying incidents. Currently, our approach has been integrated into Microsoft Azure to identify incidents. Let me introduce the backend system first. To achieve high service availability, the backend system is used to monitor key performance metrics, such as latency and reboots of each serving VM at every X minutes. When the performance metric value is greater than a predefined threshold, an issue report would be generated. The issue reports are typically bucketized at a certain granularity, such as region and storage. Automated anomaly detectors are implemented based on the volume of issue reports in each bucket. And when incidents are detected by the anomaly detectors, the support engineers would manually investigate other combinations so as to identify these incidents. However, the above approach has some pain points. First, the investigation process is ad hoc, so some incidents can be easily lost within the background noisy issue reports. Second, a lot of repetitive incidents are caused by the separated buckets. It makes the investigation process rather labor-intensive and time-consuming. So, we deploy our approach to automatically identify incidents from the issue reports filed by the backend system. Our statistics show that more than 30 incidents per month reported by our approach can be acknowledged by the production team, which greatly improve their efficiency. According to our estimation, on average, our approach helped to save 10 hours of the workloads. Despite the improved efficiency, our approach also identified incidents that are difficult to identify using conventional approaches. We now show 2 representative cases. The first case is identifying silent incidents. The silent incident means the sudden burst is buried in noisy data and cannot be easily identified. For example, in these 2 figures, the top-level curves shown as the red lines are quite flat. However, the effective combinations reported by our approach contain specific subscription IDs, which means specific VMs suffer significant performance degradation. After investigation, Our engineers find that the incidents are caused by the improper settings of these VMs. Previously, these incidents can be easily neglected and continuously affect customer experience. Our approach can effectively identify these silent incidents, help them to avoid neglection, and thus improve customer experience. The second case is a platform-related incident. These incidents are caused by software incompatibility. The figure shows the same incident in different regions. Previously, engineers have to investigate the same incident in different regions separately, while our approach can identify these incidents globally. Given the effective combination produced by our approach, engineers can quickly recognize that the incident was caused by incompatible software, which greatly improves the efficiency of troubleshooting and reduce redundant efforts. So, in conclusion, in this work, our target is identifying incidents while finding effective combinations from large-scale, multi-dimensional issue reports. We first formulate the problem as a search problem, and then we propose a meta-heuristic search framework to solve the problem. And our approach is proven to be effective and efficient in industrial practice. More details of this work can be referred in our paper and welcome to discuss. Thank you.